Thank you very much, Gabriele, for the introduction, and good morning, afternoon, evening to all the participants. So you can see my slide, right, in presentation mode, is it correct?
Yes, we can see it now, yeah.
Okay, it is good. Okay, so I don't need to say too much about myself. Gabriele has already summarized the main things. So I think I will start right away, essentially by trying and defining this strange moniker, symbolic inference in the title. That is one artificial intelligence tool that I've been developing in my group for quite a while. I mean, I didn't invent it, but we have been working a lot with this symbolic inference, and I'm going to explain what it is, since it's not really the most common tool. So to get there very quickly, I try to systematize the field by saying, first of all, we have the big container that is artificial intelligence. It includes all algorithms that mimic human intelligence. So there is not necessarily a learning step in artificial intelligence. It could be somewhat fully coded in kind of if-then rules, and this was the original artificial intelligence, let's say. A subset of artificial intelligence, machine learning, where the focus is now on the learning part. And it is a collection of algorithms where statistical learning is the focus, and really boiling down to the core, learning means regularized regression. So there is OR classification. There is a mathematical device that is called regularizer that makes it possible that one improves a model with more data. Should move, yes. A subset of machine learning that only recently has been identified, even though people have been working with this kind of tools for a while, is so-called representation learning. So there is a set of a class of machine learning algorithms that do not only learn a model, but also learn the representation. So the most say famous for sure is deep learning, where some deep neural network learns an internal representation and together with the model. So out of the input provided by the user, the neural network uses and learns some kind of function, complex function of the input, probably a subset of the input. So it can even disregard part of the input if it doesn't help for the learning. While other algorithms, they are somewhat obliged to use all the input in some sense or another. And in this class, we have representation learning. Representation learning is symbolic inference. And symbolic inference is, so inference is just another way to say learning from data. Symbolic means that we learn equations, so or inequality in other cases, in terms of mathematical expression that we can actually read and to some extent interpret. So we use rather the word explanatory, because we can look into the model and we can try to understand what's going on. And I will provide examples of this. And the advantage of this symbolic inference is that in general there are few tuning parameters, and therefore the model can be learned with few and sometimes very few data points. So we have symbolic regression, symbolic classification, and then we have also something even fancier that is symbolic descriptive rules learning. So this is something I will show if time will allow me at the end of my talk. That is a bit more abstract way of doing machine learning. So I decided to start with this because I wanted to immediately provide an application example that I hope is interesting for the audience. because it is about catalysis. And I first introduced the problem that we addressed, and then I will introduce the method that we have used to address the problem, and then its result. And then I will fall back and introduce the larger infrastructure that we are developing in order to allow for learning from data that are provided by the community rather than produced ad hoc for every new project. Okay, so back to the catalysis challenge. So I mean, the group of Matthias Schäfer, where I have been for many years at the Fritz Haber, has been always looking in heterogeneous catalysis from the theoretical level. And in this particular project, we paired up with a group of Robert Schlögl, another director of the Fritz Haber in the inorganic chemistry department. And the idea was to try and characterize material with respect to their catalytic properties in order to try and predict how to improve, for example, or in which direction one should a little bit do something to the material in order to improve its catalytic figure of merit. So as you know, catalysis is kind of one of the most important example of physical problem that go across the scales. This is why we have this diagram here. So both in terms of length scale and time scale. So the idea was to try and see if one could shortcut information on the one gets from, say, from the nanoscale analysis in order to predict the macro scale properties, rather than try and model the whole scales scenario. So to make it more precise, because of course we didn't address the whole heterogeneous catalysis realm, we focus on this reaction here. So the production of acrylic acid as a kind of precursor of many important organic compounds, and the typical full chain of reaction is described in this complex diagram, but we essentially focus on the simplified version. It should be like something showing that in this network you get these compounds as kind of milestones in the network. And because of experience and availability, we focus on a class of vanadium containing catalysts that were known previously in the literature and most importantly in the group of Robert Schlögl. So this is our data set, 9 materials. And now I'm going to explain how we can do something with 9 materials. So first of all, the materials were characterized fully from an experimental point of view. And so we have parameters that come from the fresh catalyst, the activated catalyst. So these are all different experiments that give different measurements on the same catalyst in a very curated way. So Robert Schlögl, in particular in the group of Nette Truschke, they have been quite pioneer in trying to define good practices in order to characterize fully catalyst material. And so at the end of the day, we had for each material 49 Barton surface properties that we could use as a candidate for our learning. And then we did this symbolic regression trick that I'm going to explain in the next few slides. I should say we selected one specific scalar target, so the selectivity of the acrylic acid production in the reaction. Okay, so the method. The method is it's a symbolic regression method, so we learn equations. But to do that in a treatable way, we resorted to this kind of machinery. So first of all, we say that our constituting equations, so our predictive model, is a linear combination of some basis functions. The basis functions are nonlinear functions of some input features. So here would be, so I should go back, yes, each of these 49 features that are all scalar features. And we combine them nonlinearly, and we get a lot of this function, and then we try to find the linearest function over these functions that gives the best prediction. The trick here is called compressed sensing. Okay, so the idea is that we find the linear combination that best predicts our property under the condition that only few of these basis functions are really active. So from linear algebra, this would be having a linear system where you have a huge matrix with a lot of columns and as many rows as the data points, but only few columns are selected in this expansion. How do we produce this nonlinear basis function? This is the symbolic regression idea that is pretty old, I think from the 70s, is to define a set of operators like sums and subtraction ratios and so on, and then combine them using somewhat grammatical rules, right? So if we have a sum or a subtraction, we only do that with the quantities that have the same units, so it's like length, that's why like here or energy here, and a few other things like if we do function like an exponential or logarithm, the argument should better be pure number, so unitless, and so on. And what we actually do is building this kind of so-called regression tree automatically by just combining all the features and all the operators again with these grammatical rules. So this gives birth to a huge number of candidate expressions that are combined by the algorithm. So I will not say too much about how the algorithm works. If you want to know more, we have a nice tutorial on a Jupyter notebook, and I will get back to this idea of having Jupyter notebook to present algorithm and results in a few seconds, because one thing we have been quite pioneering in the NOMAD laboratory. So to get closer to the solution, I probably forgot to say that the parameters, so the observables that we could measure of the material catalyst were at different temperatures. So here we use a flavor of this symbolic regression that is multitask. So the idea is that we learn different properties at the same time. Here, the different properties are actually the same property at different temperatures. So it gets a bit more complicated from the point of view of linear algebra, because we are learning different linear system at the same time. So we are solving different linear systems at the same time, under the constraint that the basis functions that are selected are always the same in all the linear systems. So we get that property one is a linear combination of something, some selected function. Property two is another linear combination, but with the same selected functions. And so that one can also imagine that one has a continuous property that is a function of a continuous parameter, and then the learn coefficients are a function of this continuous parameter. I mean, now let's go to the results so that these things become a little bit more clear. So we had these 9 catalysts measured at different temperatures. So what is that? 9 different temperatures. So this gives now a few more data points, not an amazing number of data points, but so this is the predicted quantity, the selectivity for acrylic production of acrylic acid, and the model learns this thing at different temperatures. So one can observe how the coefficient change as a function of temperature. And so again, there are 2 selected functions that I will discuss in the next slide. And the coefficient change is a function of temperature. So these are the actual learned coefficient, but one can also fit the curve through this coefficient. And so one has eventually a full relationship as a function of the material and the temperature. So the function of the material, I think I went back to the slides. Okay, well, sorry. There should be another slide that then comes later. 1 second. Yes, this is what I wanted to show. So let's say this is one of the two descriptors, but let's just look into that. So it is some kind of algebraic function of some of the input parameters. So this is 5 out of 49. And so some properties are mesoscopic, like the pore volume, and other are more electronic, like the work function. That, as you see, they are measured with different techniques. Having this relationship, back and forth is not working very well. Okay, I can just look into this. Stop. Okay, so this would be the diagram as a function of the two selective basis function, and the color code is the activity of the material. But more informative is when we say kind of reduce to one dimension the descriptor by taking essentially a linear combination and looking at the different temperatures. So on the y-axis, how should you read this diagram? You have the descriptor of the material. So this is a number here between 0 and 100 and something that completely identifies a single material by means of all these properties that have been selected by the model itself. And then here you have temperature. And then you see that, yeah, here is where we have the 100% selectivity. That probably is what we want. And then we have already this material that is pretty good, especially in this Goldilocks temperature here. But then one can say, yeah, maybe I'm told that this particular material could be quite expensive and not really very stable, and so on. And one could say, okay, can we change one of these other materials in order to improve the selectivity, having something a little bit better? Well, the answer is yes. This is not yet being produced, even though, I'm not so sure about the current status in the group of Robert Schlögel, but the idea was to say, okay, we could try to manufacture a similar material here with increased pore volume and this activation energy of the bulk conductivity by tampering a bit with the material, and this should improve its selectivity. Now, out of all these parameters, the methodology gives a predictive model and a way to look into this and make some useful prediction. Okay, now I move to the introduction of the infrastructure that we have been building in order to allow more and more of this analysis and discoveries. So what I'm talking about is the FAIRmat consortium now, and the idea started from the definition of these FAIR principles in 2016, where data for especially scientific analysis should be findable, accessible, interoperable, reusable, so that people can really reproduce, but also do new kind of analysis with data in science and specifically for us, material science. Okay, so everything is about metadata and ontologies, but I will not spend too much time here. So what we have is this NOMAD laboratory, NOMAD infrastructure, that is somewhat the precursor of the FAIRmat consortium, or even today we call NOMAD the infrastructure itself. And so we have a repository where we store the data, and then we read the data and transform into our internal representation. So the idea is that people do not have to comply to any standard in order to upload the data. Everything is left to parsers that could be developed by the users themselves, but so far they have been mainly developed by the team, so that people store the data in a specific way they like, and then we transform into an internal presentation that makes it easy to query via API and have a artificial intelligence tool on top of it, or just browsing the data. So for atomistic code, this is let's say easy-ish to do, because typically people would have input and output of their codes. For experimental data from electronic lab notebook, the thing is much more complicated, but the consortium is working with it. I'm not the expert in this, but I can tell something if you're interested on the experimental data and put you in contact with the expert in the team. So the origin of the NOMAD infrastructure is from 2014, actually, so even before the FAIR rules were expressed, and it was funded founded by Matthias Schäfer and Claudia Draxler. The archive, the NOMAD archive, contains, depending on how you count them, some tens of millions of calculations on different materials, even thanks to the fact that we ingested the content of the big US databases, of course, with the consent and support of the main developers of these databases. And today we have FAIRmat, that is led again by Claudia Draxler, deputy is Christoph Koch. It has many areas now. So before, NOMAD was just computation, and now we have a synthesis and experiment area. This blue background is strange. Anyway, I will go very fast here because I want to say many more things, and time is getting short. So we have a team of people working on characterizing synthesis data of materials, experimental characterization, and still computational part. So I fast forward to the computational part, where I am like the coordinator of the area, and then we have also some leaders like Silvana Botti and Kurt Kremer. And to some extent, this is the kind of direct offspring of the old NOMAD laboratory. Then we have a full area on infrastructure, so we have a large team of software developers for that, and we have an area dedicated to the actual application of the methods, as you see, in different say fields that are of scientific interest in material science, and we have an area devoted to training, and this is the full FAIRmat thing. So let me go back to this diagram, because I want to focus on this kind of use case that is the artificial intelligence toolkit, where again I have been the leader since its beginning. The idea of the artificial intelligence toolkit is to have a web-based platform where people can run essentially Jupyter notebooks in order to really learn artificial intelligence and machine learning methods based on examples from material science, and also look into really all the details of some artificial intelligence workflow in a specific publication. So this is why we have different kind of entry points, like we have tutorials, so kind of basic level or semi-basic level on some methods, but also application to actual publications here. So this is what you get if you get, I should have shown now, you get there, but yeah, you access all this by the general portal nomadlab.eu. So yeah, okay, it is important that everything of this platform as a local version that people can install on their laptop or some local server in order to manage the data, do the artificial intelligence, and so on and so forth. Okay, so yeah, the idea of the toolkit is threefold. So one is to give direct access to the data via an API in the NOMAD archive and perform the artificial intelligence analysis. The other is yeah, okay, as I already said. The other thing is to have these tutorials where people can learn methods. They could be kind of standard textbook method, but also newly introduced, like the symbolic regression tool that I have quickly presented before. And so also, as I was mentioning, notebooks for reproducing published results, so really top level results. Okay, so back to the so if you click one of these buttons here, you would be presented with a menu where you can access different methods that you can screen by method, author, and so on and so forth. So this, yeah, so you just go and try, and it doesn't require any pre-installation in your computer. You just use your web browser. Okay. Another, so now I'm moving back to example of application of our method, just to show a little bit its power and its overall philosophy. Quickly here, we were interested in predicting if materials would crystallize as perovskites or not. And the challenge was to use just information on the isolated atoms, right? So we would like to look up in a database where we have information of that isolated atoms over all the periodic table, and be able to predict if the material is or not a perovskite. This challenge, of course, has a very noble predecessor. So this Goldschmidt tolerance factor that was fancied by Goldschmidt about 100 years ago by kind of a human learning, human symbolic regression, and could say, but by some intuition and cooking, it came up with this more or less famous formula, in which one uses some specific kind of ionic radii or Shannon radii. If you want to know more, just ask. That also depend on the oxidation number, so one has to predict the oxidation number of the material, and one comes with a prediction that was pretty or fairly good. It's quite good with oxides. So if X is oxygen, and to be fair with Goldschmidt, he thought mainly about oxides. So it degrades, the performance degrades quite a lot if you go to halides, for example. So we said, okay, let's try to learn a better formula with essentially the same ingredients. And the symbolic regression method came up with this formula that has very similar ingredients. So we have the Shannon radii A and B, the one of the anion X, and now you have upfront the oxidation state that is somewhat hidden in this Shannon radii as well. And this formula becomes much more accurate, and it becomes essentially fully accurate if one gives some no-man region in between, right? So one says every material that is below a certain value and above a certain value is 100% perovskite or non-perovskite, and everything in between can be assigned a probability to be perovskite. I should have said that this is all trained on experimental data where we have like the positive and the negative. So we have a lot of AB extreme materials, and by scanning in literature, we flag them as yes perovskite, no perovskite. And now you have a formula, and you can play around with it with your mathematical tools, and you say, okay, let me say that I fix, say, the anion, and I fix the oxidation number of the big cation, the largest cations, so the one in the center of the cage. No, the one in the center of the octahedral cages. And then essentially I can browse over the elements in a continuous plot, right? So by just representing an element as a Shannon radius, you can say, okay, these are all supposed to be perovskite, and these are supposed to be non-perovskite. And indeed, whenever we tried, this was predictive properly. So this is a snapshot of the notebook. If you go to the toolkit, you will find a full notebook that introduced you to how we did this, how it was trained. You could train your own model by fiddling with the parameters of the training. Maybe you'll find something better than what we found. But in any case, you can find exactly these and produce exactly the same plots if you want. Okay, another advanced example of our method is like, so we try to push to the limit, or at least forward, the idea that, okay, you get a method, but then you can inspect the method and you can learn something more than just having a prediction with some root mean square error or mean absolute error, whatever you publish, and you say, okay, look, I can predict my thing plus minus 0.1% or whatever. Let me explain what I mean by showing the example. Okay, here we were interested in predicting the lattice thermal conductivity of some class of materials, and again using as cheap as possible features, right? So here is not anymore just the atomic constituent parameters. As you see, it will be a bit more, but still much less than doing, say, a full prediction of the thermal conductivity here on a theoretical basis, computational basis. And so we get our model where we predict with our method the thermal conductivity, and this is the ground truth. Figure of net is great. There are not very, couple of outliers probably, but very close to the ideal prediction. So very, very good model. The model itself is simplish. If you would think to train some neural network or a regression tree, the model would be much, much more complicated to look at. And here, I should have put a legenda probably, but okay, what enters is the average mass of the material. So this comes from the atoms, the molar volume. So this needs one needs to know the relaxed structure, and then you get something from the phonons. So you need the harmonic phonons, and look at the spread of the phonon distribution, density of state, and this is the most expensive one. So this sigma A was introduced. Where are the authors? Okay, I should have. They will come later. The co-authors. So was introduced previously in the group Mattia Scherper by Christian Carbonio and co-workers. This anharmonicity factor. This requires to sample it to be the potential energy surface in order to assess how anharmonic is a material. Okay. But then we look into this prediction and say, okay, can we make it a bit more understandable? So I skipped the math here. So there is a thing called Sobol indices that look into the how much a variable, here a feature, affect functions in a local way. Now there are several methods to do that. Very popular in machine learning. Most of them do not account for correlation among properties. So you would disregard the correlations, and this gives typically not very nice predictions. And here, by applying this fancy tool, we ended up by identifying as a maximally independent but also maximally important features, this molar volume, anharmonicity factor, and essentially the Baye temperature. And this gives an idea that okay, this would be a representation of the three-dimensional manifold in which the material lives. That one could say, okay, let's say we are interested in materials with low thermal conductivity, and if we look at the distribution of this material, we could say, okay, but if we filter out material that have, let's say, so you have the thermal conductivity on this axis for all three diagrams. So basically, if you concentrate on materials that have large molar volume, small Baye temperature, and large anharmonicity, you would essentially get to this low thermal conductivity material. Also, you know how much is the cost of evaluating these properties. So this knowledge gives a kind of a hint in order to stratify your search. Namely, you have seen this kind of search funnel many times in material science, especially recently. But the catch here is that this was not designed by just thinking of the material, but after the machine learning model. So after the model and its analysis, we say, okay, we first prescreen by this structural parameter, then this harmonic phonon parameter, and then this parameter that requires some molecular dynamics. So only the materials that pass the cheap test, the cheaper test, will end up to the final thing, and then you can predict your thermoconductivity and be happy or not. Also, this as a notebook, so you can go there. But the main message of this kind of semi-in-depth analysis of this work is to say that we can essentially arrive at the design of a high-throughput workflow after the analysis, the machine learning analysis. Now imagine the ideal case scenario that these data are in the archive. Could be the NOMAD archive, but any archive that you can browse with suitable API. And then you do this kind of rough modeling, or maybe not so rough, and then you do this analysis, and you come up with the traditional afternoon with a way to do the screening of materials for lower thermoconductivity, and then you can perform it. Now, what time is it? Okay, I'm going to this. Now I'm showing a little bit of another side of symbolic inference, and this is about learning descriptive rules. So we try whether to predict properties to describe part subset of the data set that has some peculiar property. And to fix the idea, think about some kind of property of some system, of some material, where you have as many as 6 data points, and you try to fit a linear model, and this will be your global model. And then you say, well, that if you have grounds to say that actually there are 2 subsets of material, now with as many as 3 data points, of course this is just a cartoon, you actually have a completely different predictive model with actually the opposite trend with respect to the correlation between this property Y1 and Y2. So this is the core of this symbolic regression. We have a very nice tutorial on that, I must say. But let's see where we applied it, and then let's be back to Catalyst. The idea here was to find a hint on better catalysts for CO2 reduction. Yes. So this is the kind of reaction diagram for you want to go from CO2 to useful chemicals here. And here we have theoretical data. We characterize a surface and onto which a single CO2 molecule was absorbed. And we were interested to see if there is some signal that tells us just by looking at the pristine surface if the material is likely to be a good catalyst for CO2. So to be a good catalyst, the material should be activated, the molecule actually should be activated, the complex should be activated. And how a CO2 molecule gets activated? Well, by bending the OCO bond and or elongating the C, either or both CO bonds, because eventually you have to cleave the oxygen atoms in order to get something going on. And the big question is whether it is more important as a descriptor, the bending of the angle or the elongation of the bonds, and at the same time, if we could predict what happens just by looking at some property of the pristine surface. So even here, we have a set of properties collected over all the data set. And then we apply this subgroup discovery technique that actually tries to find if there is a subset of data that has something peculiar with respect to some target property. Here would be the distribution of the bending angle or the distribution of bond lengths. And then we say, okay, here we look essentially over all possible subset of data, and then we see which subset has unusually large CO bond, and so on and so forth. And in the end, we want to find a description of these subsets such that we can immediately understand if the material belongs or not to this subset. Only afterwards, we check from literature if these materials are known to be or not good catalyst for CO2 activation reaction. So in short, what happens is that if we represent our system by its distribution in absorption energy, the methodology identifies a subset of material that has an unusually small bending angle after absorption of CO angle, that is the blue subgroup, and it's another subset that has an unusually large CO elongation bond. Now, if you look at this plot and you are acquainted with Sabatier principle, you may immediately understand that the green subgroup is the good one, because these material here tend to be quite strongly bound to the surface, while these ones are not so strongly bound, so probably they are better for being a good catalyst. It turns out that when we check, that's the case. Every material that landed in this subgroup was found to be a good catalyst, but no information about being or not good catalyst was used in the training of this methodology, and vice versa. So none of the small angle was a good. So those that were in the small angle, but not in the long angle, long bond, were good catalysts. So basically, they tend to poison the surface. Yeah, so this was the prediction in terms of description of the material, and we have a tutorial also for this, where you can reproduce the results and go into more detail of what's happening. We have more applications that I want to skip. Yeah, essentially that's it. I can stop here. So there is a clearly long list of people that have been contributed. The methodology started almost 10 years ago now, discussing with Jan Wieberer, who's a mathematician, when we set up the basics of this methodology. Then Runhai was postdoc with me some time ago, and now is a professor in Shanghai, made the big step of the CISO approach for many more features and so on. And then that is okay. Big mistake for me. And then now we have the code with which we have done the most recent application, developed by Tom Purcell, who is not listed here. Apologies to him, but okay. You can find the code. If you ask me, it's in any case called CISO++. It's pretty easy to find. Yeah, I thank you for your attention, and I stop here.